Okay, so this time in this example 14 of Chapter 5, Section 3, Perpetuities, we're going to look at a perpetuity where we have an endowment. Okay, so we're given that the endowment is $80,000 and it's invested at 4.9% interest, compounded quarterly. Okay, and we want to determine the size of the yearly payment, so again, they don't match. That can be made indefinitely, so indefinitely is that keyword for perpetuity, from the endowment when the first payment is made a year from now or 5 years from now. So again, we have the starting immediately, and then we have the deferred. Okay, so what the big idea here is here we're trying to find the size of the yearly payment. So we're trying to find R. So instead of doing the A infinity, we're going to work backwards. Okay, now if A infinity is at 80,000, like it would be here, and on our timeline we have 80,000, and then in 1 year where we're going to get a payment, and then the second year we're going to get a payment. So this is our kind of setup for this. Okay, and again we have quarterly and then yearly, so we know that 80,000 has to be equal to R over 1 plus, here our rate is 0.049 quarterly, so that tells us that I is 0.049 over 4. And that's going to be 4 times a year, okay, because our interest happens 4 times, so N here is 4 over 1, because this is how our payments, how frequent our payments are, this is how frequent our interest is. Okay, so that means we're going to do it 4 times in that year. So what we're going to do is we're going to find the coefficient and then multiply this over. Okay, so really it's just going to be R equals 80,000 times 1 plus 0.049 over 4 to the 4 minus 1. So you could find this coefficient 1 over this and then divide by it. Or you could find what this number is and then multiply 180 by it. It's not really a separate formula because we're just manipulating the one formula, so I don't think your book has this one as a separate formula. Or you can always add it to your formula sheet. So that means our regular payment is going to be $3,992.62, rounding to the nearest penny. Okay, now we're going to work this 5 years from now, so kind of a mix of this one and this one. So this is going to be a separate timeline because it's different right here, and again it's going to go on forever because we have those indefinite payments. So we have AN deferred, it's going to be our 80,000. Okay, and then in 5 years we start payments. And it's not always 5 years. These two examples that we do just happen to be 5 years. But the idea here is that, again, we set it up just like an AN deferred problem. So 80,000 equals R over 1 plus 0.049 over 4 to the 4 minus 1. So again, that's going to match what we did over here. Times 1 plus 0.049 over 4 to the negative, and now we have to figure out what that is. So here are total compoundings that we do. Would be 5 times 4, so that's 20. So that means if n plus p equals 20, n is 4, so we have 4 plus p equals 20, that tells us that p is 16, so this would be our 16. Alright, so in this one, I'm going to take this divided by my denominator, and then I'm going to get my coefficient for r. So we have 80,000 equals r times some number, and then we'll divide by that. So I'm going to take this piece, 1 plus 0.049 over 4 to the negative 16, because that's on the top. This would be over 1. And I'm just going to add an extra set of parentheses just so I know my calculator won't mess this up. And then on the bottom, 1 plus 0.049 over 4 to the 4 minus 1. And again, double set of parentheses there. So our coefficient is 16.49 and change. And we're not going to round that. 80,000 divided by answer. So we get $4,851 and 35 cents, rounding to the nearest penny, which again is a much larger piece there, because that means per month we get an extra about $800, or sorry, per year.